Welcome everybody. This is our Fallbrook Climate Action Team meeting featuring Jonathan Cole today. Jonathan is a professor emeritus at Mira Costa College, and he was speaking to us a year ago about hotspots, and everybody was so impressed with him. We thought we really need to have him come back and explain our weather patterns currently, because you hear people talking about, well, if we have global warming, why is it so cold outside? You see that a lot on Nextdoor. So for those of you who've never been to one of our FCAT meetings, we're just a group of local climate activists in Fallbrook, and we put on these monthly presentations on Zoom to reduce our carbon footprint, to talk about various aspects of climate change and mitigation. And if you're interested in being a volunteer to help get the word out, make reminder phone calls before our meetings, or something else that you might want to help out with, just let me know in the chat and I'll contact you about that later. So with that being said, I'm going to turn it over to Jonathan.
All right, well, thanks, Joy. Thanks for that introduction. And as Joy said, I'm Jonathan Cole, and I taught physics at Mira Costa for about 36 years, and also developed a course in climate change. So today, last time we talked about hotspots, about heat waves and extreme temperatures, and looked at it from a pretty global perspective. This time we're going to be talking about precipitation, moisture, and we're going to do that from a more California-centric point of view this time, just because there's so much going on right here in California, and that's where a lot of the questions are coming from. So I'm going to go ahead and share my screen. And hopefully you can all see that. So again, this was kind of the question, is people saying, hey, if the earth is warming, how come we've got all this snow? And we do have a lot of snow. This is a little video that was taken by the New York Times. This is on a flight over the Sierras, basically with a plane that's using remote sensors to measure the snowpack. And they've confirmed that we do have a pretty large snowpack here. In fact, they say among the highest ever recorded. The reason they can't say exactly is because it gets really hard if you go back decades to try to compare. There's different coverage, different methods used, but certainly within the last 20 years or so, this is the highest snowpack that we've seen. And this is just a little graph. So I'm not sure if you can make out the faint gray lines. Those are different years since 2004. The darker blue-green lines are the last 3 years when we've had very low snowpack. And then the black line is this year. And this year's snowpack is, for this time of year, the highest that's been recorded in the last 20 years at least. So this is probably at least 10% above the previous records. So we've got a significant amount of snow, and that's had a lot of different impacts on the state. Some folks have really tried to make the best of it. So, snow kayaking in Lake Tahoe. So, if you're into that. But a lot of the impacts, of course, are negative. We heard a lot of stories about folks in places like Mammoth Lakes, Big Bear, who were trapped inside their houses by just these incredible depths of snow. And of course, the weight of snow on all these roofs has caused a lot of issues. So we had a lot of buildings collapse. This is just an example of a building in South Lake Tahoe where the weight of snow on the roof was just way beyond anything it was ever designed for. So the building just collapsed, the roof caved in. More other issues are that weight on water pipes and gas pipes can cause real problems. This house, the gas pipe was cracked, so gas started leaking, and there was a spark, house exploded. So a lot of impacts from the heavy snow. But of course, folks who are skeptical, deniers, whatever term you want to use about global warming, kind of point at this and say, oh, look, it's cold, there's snow, therefore global warming's a myth. And in fact, one of the motivators for this talk was this item I ran across. This is a conservative site called the Babylon Bee. And so, they're having a little fun being snarky, and talked about California covered in 6 feet of global warming, and everybody panicked because of the deep coverage of global warming. Yeah, pointing at snow and saying, look, snow, therefore no global warming. There's a long history of this. One of the most famous or infamous incidents was about 8 years ago. Senator Inhofe of Oklahoma, James Inhofe of Oklahoma, basically brought a snowball onto the floor of the Senate. And we think we've got the audio working now, so hopefully you can hear this. If not, just enjoy the video.
Of national attention, and in case we have forgotten, because we keep hearing that 2014 has been the warmest year on record, I asked the chair, you know what this is? It's a snowball. And that's just from outside here. So it's very, very cold out, very unseasonal. So here, Mr. President, catch this.
So I guess the little smirk at the end that really does it for me. But were you able to hear that, the audio on that? I see some nodding.
Yes.
Okay, good.
Yes.
Okay. So this was a really famous incident of using snow as an example. And Inhofe is, of course, recently retired, but was one of the biggest climate skeptics, climate deniers in Congress. And he's from Oklahoma. He really ought to know his snow a little better than that. There's different kinds of snow. So there's no audio on this one, but this is just a piece from the Weather Channel talking about the difference between wet and dry snow. When it's really cold, you get that kind of dry, powdery snow that skiers really like. It's also lighter weight. It's easier to shovel. I grew up in Colorado, so I know that when it's really cold, you get that kind of dry, powdery snow. And the wet snow, that's great for snowballs. So that's the picture on the left there. Wet snow packs really easily, but it's not so great for, but it's not as good for skiing. And this is another visual. This is from a TV station in Milwaukee, where again, they know from snow, and they talk about wet snow versus dry snow, and the fact that the wet snow that you get, this is when the temperature is in the 30s. So temperatures typically above freezing. That produces that really slushy wet snow that makes great snowballs, like the one Inhofe brought in. And that carries a lot of water. So 5 inches of snow you might only need 5 inches of snow to melt down to 1 inch of rain. Whereas the dry snow, that's what you get when it's really cold. So if it was really super cold outside, it would be dry snow, not wet snow. And he wouldn't have been able to pack that snowball. So just point out that snow is not necessarily a sign of extreme cold. And in fact, wet snow means it's not that cold, it's above freezing. Inhofe also mentioned in there, this was in February 2015, he was speaking. He mentioned 2014 was the warmest year on record. And we do need to point out that, in fact, temperatures are going up. And so when he was speaking in 2014 was then the warmest year that anybody had ever recorded, looking at the global average. The year he spoke, 2015, was even warmer. It turned out by the end of the year that it was significantly warmer, and 0.2 of a degree Celsius or 0.3 of a degree Fahrenheit. That's a big difference when you're talking about the global average. So that was a much warmer year even than 2014 had been. Just for comparison, the most recent year, 2022, fell kind of in between those two. But the key point is that if we look at temperature, 2022 is the red bar. This is just a bar chart comparing temperatures to the 20th century average. Red is warmer than 20th century average. And we know that every year since the late 70s has been warmer than that 20th century average, and has continued to get warmer and warmer. And if we look at the level in 2014, every year since 2014 has been warmer than 2014, and 2014 was previously the warmest year on record. So there's no question that global warming is happening. The Earth is continuing to get warmer, and that a snowball doesn't disprove that. Also, you do notice that it's not every single year gets warmer. There's ups and downs. Lots of cycles come into this, especially El Nino, La Nina cycles, but the overall trend is pretty clear. If we look at a shorter period, the most recent month, this is the temperature difference from average. Here they're comparing to the average from about 1981 to 2010. Red is warmer than that average. Blue is colder. And so we see there's most of the globe is warmer than it was in previous Marches over that base. And significantly warmer in Asia, for example. Recently, just a couple of weeks ago, Thailand had their warmest temperature ever on record, about 115 degrees. But you do notice that the West Coast and California are cold. We're in a cold spot. We did have a cold winter here. But the fact that one area is cold doesn't dispute the fact that the globe as a whole is getting warmer. So we'll come back and talk a little bit about why that cold spot's there, but I want to step back a little bit and look more at the basics of what's going on, the basics of moisture in the atmosphere. And one of the predictions of climate change, which we have been observing, is that we get both enhanced rainfall and enhanced drought. And so things get wetter and drier. And again, climate skeptics like to say, wait a minute, you're just sort of saying anything could be global warming. But there really is solid science behind this idea. And this all starts with, of course, the water cycle, which most of us have seen in school at some point, a diagram something like this. And the basic idea here is this is all driven, of course, by our friend Mr. Sun, which is why they put him up in the corner there. The sun provides energy that then causes evaporation. Most of the earth, of course, is covered with water, so we get evaporation from the surface of the ocean. Over the land, when we look at this, we talk about evapotranspiration, and this is evaporation when you take into account plants. Plants pull water out of the soil, it's spread through their leaves. Some water will escape through little holes in leaves called stomata. So it turns out plants speed up that evaporation process. And then sublimation, we won't worry too much about. That's just ice, like in high glaciers, going directly into water. So the sun drives all this evaporation, evapotranspiration of water into the atmosphere. And then that water ends up getting stored some of the water is in the atmosphere at any particular time. There's water stored in the atmosphere. It doesn't stay there, but it will rain out eventually. But at any particular time, there's something like 14 trillion tons of water in the atmosphere. If you put in a cube, it would be a cube about 15 miles on a side. So that's a pretty large amount of water. On the other hand, that's tiny compared to the ocean. The ocean is 2 miles deep, and it covers 70% of the earth. So 15 cubic miles, that turns out to be about 1/1000th of 1%. So most of the water on earth, most of the time, is in the ocean, but there is some in the atmosphere, and that's a significant driver for climate and weather on earth. And water, as we'll see, the air can hold only a certain amount of moisture. And once you get more moisture than the atmosphere can hold, then that water basically falls out as precipitation, as rain and snow. So basically, it's just a function of how much water the atmosphere can hold. It tells us how much water there is up there. And the physics of this, I taught physics, so I've got to give you a little bit of physics here. This is really just the basic physics of water. And this has been known for almost 200 years. So we've got these two guys. Benoit Clapeyron is a French physicist. Rudolf Clausius was a German physicist. And in the 1830s, Clapeyron worked out, he just looked at the basic physics. How much energy does it take to evaporate water? How much can the atmosphere hold? And he worked out the basic relationship. Clausius, who's very famous in physics and in thermodynamics, the study of heat, worked out a more exact mathematical equation. And that's kind of what this graph is showing here. And this is called the Clausius-Clapeyron relation. So what this says is just basically along the bottom here, we've got temperature. So it's saying as the temperature goes up, as things get warmer, the atmosphere can hold more water. And I've kind of simplified this by just saying wetter. Warmer means wetter. And this is something most of us have experienced somewhere along the way. Warmer air holds more water. More exactly, warmer air can hold more water. So this graph is not saying that's how much water is going to be there. It's saying that's the maximum amount that can hold. And I've got this in these weird units because scientists always love weird units of millimeters per cubic meter. So let's break that down a little bit. A cubic meter basically just means a cube about 40 inches on a side. So a little bit bigger than I can show on the screen here. But if you think of a cube 40 inches on a side filled with air, and you say, how much water could that hold? So for example, if the air was a little above 50 degrees, it turns out it can hold about 10 millimeters. So the maximum amount of water we could evaporate into that air would be 10 millimeters. Or if we condensed out all the water, it would be 10 milliliters. And that's 5 milliliters is about a teaspoon. So 10 milliliters is about 2 teaspoons. So 2 teaspoons of water in a block of air about 40 inches on a side. That what this relationship says is as we get warmer, that goes up. So if we warm the air from a little above 50 to a little bit above 70, like 73 degrees, it can hold twice as much water. So if we go from 50 to 70, we basically doubled the amount of water. Now it's going to hold 20 milliliters or about 4 teaspoons of water. So the key point here is just warmer air can hold more water. That doesn't mean it's always going to hold more water, because how much water it's going to hold depends on what's available. It's going to depend on what the source of water is. But overall, most of the Earth is over the ocean, so it can suck up as much water as it needs. And it turns out that you can kind of summarize this. The rule of thumb is that every time the temperature goes up by about 1 degree Fahrenheit, the air has the capacity to hold about 4% more water. And since most of the air is over the ocean, where there's plenty of water to evaporate, it will take on about 4% more water. We also know, compared to late 1800s, that the Earth has warmed on average by about 2 degrees Celsius because of the greenhouse gases we're putting in the atmosphere. And that means that with 2 degrees Fahrenheit, the Earth is currently holding about 8% more water than it did in the pre-industrial era. So this is a big factor in driving all this rain, all this snow we've been seeing. The warmer atmosphere is holding more water, and that's about 8% more water than it had in pre-industrial times. That's more water to basically dump down on the surface. Again, this is capacity, so just a little bit of terminology here. Let's kind of make this more concrete. Suppose I had a packet of air, cubic meter, that was at 73 degrees Fahrenheit. And I picked that because it gave me a nice round number of capacity. That's 20 milliliters, or about 4 teaspoons of water could go into that. That's the capacity. Suppose we're over land, though, where you don't always have all the water you need. And one particular, just as an example, and I just made this number up to give a particular example, suppose that packet of air, instead of holding 20 milliliters, only had 16 milliliters. Now it's only got 16, it's got 80% of the capacity. And that's what we talk about on the weather report when they talk about the humidity or the relative humidity. 80% relative humidity means that the atmosphere can hold that the atmosphere is holding about 80% of the water that it could hold. So what happens if we heat up the air? Well, we said if we heat it up, for every degree Fahrenheit we go up, we get about 4% more water capacity. Suppose we heat it 5 degrees. 5 degrees times 4%, that's about 20% more water that it could hold. So now that same cubic meter of air at 78 degrees Fahrenheit could hold not 20, but 24 milliliters. So just almost another extra teaspoon of water there. Well, suppose we heat it up, but we don't provide any extra water. We're still in the same place. We haven't put any extra water into it. So it still only has the 16 that it started out with. So we warmed it up. Now it's still only got 16 milliliters, but it could hold 24. So now the humidity has gone down. The air is drier in the sense that it's a smaller percent of the maximum it can hold. And I know I'm throwing a lot of numbers at you here, but we're almost to the end here. So the key idea here is that as we heat the air up, if we don't put more water in, there's going to be more excess capacity for that. And physicists, the way physicists talk about this is in terms of the deficit, the water vapor deficit. And we'd say, okay, at 73 degrees Fahrenheit, we could add another 4 milliliters of water into that air to get it to saturation. But at 78%, at 78 degrees, it would need 8 milliliters. It'd need about twice as much water to get it up to saturation. So we think of this as the air is thirstier. It can suck up more water. So we've got thirstier air that we're looking at. And the fancy term for this that physicists and climate scientists use is vapor pressure deficit, because it's water vapor deficit, and they measure water vapor and pressure units, or VPD. And I promise that's the only really jargony thing I'm going to throw at you today. So VPD, we can just think of that as measuring how thirsty the atmosphere is, how much more water it can take up. The reason I've gone on and on about this, the reason it's important is because there's two ways that places get drier. One is that they get less rainfall. There's less water coming down out of the sky. But the other is that you're getting more evaporation. You're losing water faster. And vapor pressure deficit is one way to measure that evaporation. So as the earth gets warmer, we get more evaporation. The air is thirstier, so it picks up more water. So it's holding more water, and when it rains, more comes down. So that's why you can get both wetter and drier. So in areas where you get evaporation going on, that evaporation is going to kick up. And that's a source of drying that's just as important as precipitation changes. So that's the basic idea. You know, the big moral of the story is that when we're talking about water and droughts, we don't just want to look at precipitation, we need to look at evaporation too. That's a major factor going on. So how is climate change impacting all of this? So what's climate change doing with this? And one of the important things is when we talk about climate change, we're not talking about a single year or a very short period of time. We're talking about a long period of time. The longer the period you look at, the different trends are going to emerge. So for example, this is from the New York Times looking at California, and this was published in January. So on the left side, they're talking about what happened in the last month. By the last month, meaning December, January, when we had those huge rains, all those downpours. And if you look at the scale up above, what you can see is all that blue-green means wetter. And it means that in this case, we have places getting twice as much, 3 times as much, some cases 4 times as much rain as they would usually get during that month over the average from 1991 to 2020. So way above average rainfall. That's if you look at 1 month. But if you average over 3 years, including that last wet month, that's the graph on the right. We can see that there, the picture is a little different. A lot of places are still, even with all that rain in the last month, over 3 years, they're still below the average. So basically there's the short-term trends, like all the rain we're getting, and there's the long-term trends. And climate scientists tend to think about really long-term trends. A minimum of 30 years is what they usually look at. And this is the work that I've been doing with Professor Ramanathan at Scripps. So we've been looking at changes over 40 years. And in this graph, we're looking at 1981 to 2020. So these are 40-year changes. Here we're looking at the change in precipitation, change in rainfall. And you could look at the amount of precipitation, but we're looking at it as the percent change. And this is sort of the average, smoothing out all the changes because it bounces up and down a lot. Precipitation is really variable. But if we kind of smooth that out, we say, is there any long-term trend? And we see different places have different trends. So for example, along the southern rim of the Sahara and the Sahel in Africa, right in the middle there, you see all that dark green. Those are areas that were wetter, up to 32% wetter. So a significant increase in rainfall. Not that they got a lot of rainfall to start with, but they did get an increase, and that increase the increase shows up as a big percent increase. If you look on the other hand at Southwest around California, over there on the left side of the map, you can see a significant decrease in precipitation. So there's been a drying trend in terms of lower precipitation. So different places, some places more precipitation, some places less. Well, what about the evaporation side? What's going on with evaporation? So for that, we looked at that vapor pressure deficit, VPD, and we measured the percent change there. And if we look at that, it's a different picture. And what we see is almost every place is getting an increase in VPD. You've just got a few places in green, like up in Canada. That's because even though it's warmer and there's more evaporation, enough moist air has come in, probably from circulation changes associated with melting ice in the Arctic, to compensate for that. But most of the planet is showing increase in evaporation, especially over Europe, China, places like that. And then what we do is we put those two together. We say, what's the difference? And again, on all these maps, green means wetter, brown means drier. So he said, let's combine that. Let's combine the increase in evaporation with a decrease in rainfall, or vice versa, and look at the combined percent change. And this gives us the idea behind this is we're looking to identify areas that have significant drying trends. And so now this picture really emerges where we're looking at both precipitation and evaporation. And we can see that there's really big drying trends in the Western United States, in Europe, especially around France, where they've had a lot of forest fires recently. You can see some around the tip of South Africa. Cape Town has had major water shortages in the past few years. Southeast Australia, where there have been forest fires, and water shortages also in China. So a lot of areas that are hotspots, and that's kind of what we're looking at in our study. And we're going to be starting to look at comparing that with models and see how the computer model projections for the future, what those predict about those drying spots. So if we just blow up California, this is the combined change around California. And again, we see that pretty much the whole state is experiencing drying, really extreme drying around the deserts, the Mojave, Sonoran deserts, places like that, but drying pretty much every place. And this is, of course, a factor behind things like the wildfires that we've been experiencing, because basically the forests are drying out and become much more susceptible to fire. Any kind of fire that gets started, it's going to spread fairly quickly. And it turns out that if you look at the factors, Southern California, this is primarily driven by lower precipitation. Northern California, evaporation is a bigger factor. But this is not just California, it's the whole West. And of course, this is a big factor behind what it's been in the news a lot, the Colorado River drying up. And the agreement on the Colorado River, how we share the water, goes back to about 100 years. And it's in trouble, partly because they overestimated the total amount of water that would be in the river to begin with. And then on top of that, because the river flow is cutting down. And just like we said, for every degree Fahrenheit that goes up, there's about 4% less moisture in the atmosphere. That turns out to apply to the Colorado River too. Every degree Fahrenheit the temperature goes up, there's about 4% less water flowing through the river. So this is a significant problem. So we've got this long-term drying trend, but yet we got short-term, we got all this snow. So what's going on with that? one thing to notice is that while California got a lot of snow, other places got less than usual. So this is a 1 year that basically when we look at last year, this is kind of a 1 year anomaly. Even though if you looked at those maps, the east tends to be getting wetter and the west tends to be getting drier. This winter, there was the red-brown areas are areas where they had less snow than usual. So all through New York, at the Atlantic coast, a lot less snow than usual. California and the West, a lot more snow than usual. Also, as was mentioned, it was colder than usual, as we saw in that graph before. And a big factor in that is the fact that there was all this moisture in the soil. So when the sun shines, some of that energy from the sun is going into evaporating the water because there's so much moisture. There's a lot more water to absorb that energy, and as it evaporates, and that means there's less energy left over for heating the land. So the land doesn't heat up as much. So one big factor in the cold temperatures we've had over the past few months is that there's so much moisture, and the moisture is basically keeping those temperatures down. So cold and snowy in the west, but warmer than usual and much less snowy in the east. So why are we getting this pattern? Why is it so different from usual? And why do we get hit by so much moisture? Weather is very complicated. There's lots of pieces to the answer. But one piece of the answer is this term that we've all come to know and hate, which is atmospheric rivers. I think almost everybody at some point has heard about, oh, we've got another atmospheric river coming in. So let's talk a little bit about this. So what we've been talking about so far is just the basic amount of moisture the atmosphere can hold. But it's not really evenly distributed all through the atmosphere. And it turns out that it's concentrated in what are called atmospheric rivers. So here we see this big plume of white. This is just clouds, moisture, rain over the Pacific. And this one is from 2019. This one is heading in more towards Oregon, Northern California. We had a lot hitting in Southern California. These atmospheric rivers, this is an animation from a couple years earlier from 2017. So this is showing how the atmospheric rivers work. And so we've got that kind of blue-green plume of water and moisture, and this is looping over about 3 days. So it'll go through about 3 days and then jump back. So what we're seeing is down towards the bottom of the picture, closer to the equator, that's where we're getting all this heat evaporating water from the ocean. So we get much stronger evaporation over the equator, or where the sun is focusing its rays. And some of that then, through the local circulation patterns, gets pulled off into these long plumes. These are around 100 miles wide typically. And it turns out that something like 90 or 95% of the moisture that gets transported across the Pacific at middle latitudes, like where California is in these atmospheric rivers. So basically, whether you get a lot of rain or very little just depends on where the atmospheric rivers hit. And we got hit with a lot of atmospheric rivers this year. And when the atmospheric river hits, basically it carries all this moisture in. As we go up over the Sierras, as the air is forced upwards heading towards the Sierras, it cools down. And we just talked about cooler air can hold less water. So air that wasn't saturated, as it cools down, rises and cools down, now becomes saturated, and some of that moisture drops out in the form of rain or snow over the Sierras. So that was the source. It was atmospheric rivers heating us over and over again, and atmospheric rivers now holding more water than they would have 20, 40 years ago because the globe is warmer. And this is just a chart showing some of the significant atmospheric rivers that hit. And this, of course, wasn't just California, Oregon, Washington. It was all along the West Coast we were hit by these. But the Center for Western Weather and Water Extremes at Scripps, who study these kinds of extremes, say that there were about 31 significant atmospheric rivers that we were hit with over the winter of 2022-23, this last winter. And that's something like 3 times what we usually get. So then the next question obviously is why? Why did we get hit by more this year? The well-considered scientific answer is we don't know yet. We're not sure yet. There's a lot of study going into this right now. We've had an unusual, we had a La Nina, we had what they called, you may have heard triple dip La Nina, which means colder water in the Pacific than usual. And that stuck around longer than usual. And this year we're transitioning from a La Nina to an El Nino, and which means warmer water in the Pacific. And that flip may have something to do with shifting circulation patterns. So we got hit more with atmospheric rivers. Some people think, you may remember that massive volcanic eruption in Tonga several months back. Some people think that the particles that blew into the atmosphere, they provide more condensation, what's called condensation nuclei. Basically, rain can condense around those, and that may be a factor. So the scientists are still looking into the explanation for why so many atmospheric rivers. But we do know that a big factor in why the atmospheric rivers carried so much moisture is the warmer air from climate change. So of course, these atmospheric rivers had a lot of impacts, and we had some really beautiful days. The rain washed out the air, we had snow on the mountains, everything was really beautiful. Over LA, this is the Eastern Sierras, just really dramatic snow pictures. And that, of course, has led to really significant wildflower blooms. And I know we had a couple of folks at the beginning talking about being out to see the blooms out in the desert. So I hope other folks, I didn't this year, but I hope folks got a chance to get out and see some of those blooms, because in some areas it's very spectacular. Also, of course, it's just been nice to see green hillsides, these really lush green hillsides that you get in a year with a lot of rain. So it's not as though all the impacts are negative, although if your house blew up in Lake Tahoe, you're probably not too happy about this. And also, if you're, say, a firefighter or a wildfire management expert looking at these lush hillsides, we remember that if we get a dry summer, come September, come October, there's a lot more fuel to burn. So it depends a lot on specific conditions of temperature and moisture. But if we have a hot, dry summer, we could have a big wildfire season. We were very lucky with the last wildfire season. Hopefully we'll be lucky again, just hard to say. And of course that has impacts on air quality, big impacts on folks living in those areas. So there's always, this is one of the consequences of a very lush winter. We also know that there was significant storm damage from all the energy and the moisture in those atmospheric rivers. You probably remember the pier at Aptos near Santa Cruz that was heavily damaged, and they've decided that it's going to be demolished. They just can't afford to rebuild it. Or closer to home for me, I live in San Clemente. And there's along the left side of this picture, you can see there's a railroad track, and next to it, there's the beach trail. I walk that beach trail quite a bit, and I always look up at those houses thinking, who would be crazy enough to put a house at the edge of an eroding hillside? These houses were red tagged. Fortunately for the owners, I've heard that the houses themselves are actually okay. They've been determined to be habitable, which surprised me, but it's apparently true. So they've been able to move back in, but obviously they've been told not to fill that pool again. There's those direct storm impacts. Also, of course, all the rain falling. This is in Northern California, and this has been an issue. Flooded fields have been a big issue for farmers. On the other hand, kind of going back and forth, the good news, bad news. On the other hand, this has really reduced the drought. Lots of different ways of measuring drought, and this is an important thing when we talk about drought. People mean different things when they say it. And the way I've been studying it is looking at precipitation and evaporation. Another way to look at it is measuring the moisture in the soil, and that can change more rapidly. And that's what these drought maps that you often see from US Drought Monitor show. So this is basically measuring the amount of moisture in the soil. 6 months ago, the Central Valley was all in extreme, or in the center in exceptional drought, really severe drought. If we look at the update from last week, almost no drought in the center of the state, again, measured in terms of soil moisture, the amount of moisture in the soil, just a little bit around the north and the southeast edges. So the drought has really been pushed back. That doesn't mean we're not still in a long-term drought. It would take several years of above average rainfall to get us out of long-term drought. But a lot of the reservoirs have refilled. So this is a plot, the green, the pale green shading shows what the historical average is. And then the green lines show the last couple of years. And we see that Oroville, for example, was way below its historical average. And now it's about 15% above that. So this was Lake Oroville a couple of years ago. And this was Lake Oroville a month ago. So we've seen these really dramatic differences. So, you know, it's great. The reservoirs are filling up again, and we've got water. On the other hand, again, it gets kind of good news, bad news. On this graph, the little blocky shaded areas show kind of historical averages again. The darker blue at the bottom is what's normally in the reservoirs. And then the lighter blue shading just above that is what happens when you add the snowpack. And what we can see is that the snowpack starting around the end of the year, December or so, starts building up, adding water storage. So we get more water storage. Peaks about April, snow starts to melt, that goes back off. But typically maybe an extra 50–60% of water stored in the snowpack. And so we don't have to start drawing down the reservoirs because we can use snow melt. In recent years, we haven't been able to supply nearly as much water because of the drought, because there hasn't been as much snow melt. This year, again, be careful what you wish for. Look at that snowpack plus reservoirs line, the light blue line just shooting way up there. And that shows we have way more moisture in the snowpack than normal, and more in the snowpack than there is in the reservoirs right now. If that melts slowly, gently, gradually, that provides a lot of extra water. The concern, however, is that it could melt fast, and people are talking about the big melt and talking about flooding risk, especially in the Central Valley. So looking at the outlook for flooding. And just today, this article in LA Times, this is pretty timely. This was today, they said that basically tomorrow, they expect a heat wave to move through the Central Valley, temperatures in the 80s and 90s, overnight temperatures not dropping below freezing at a lot of elevations. So the melt could really accelerate, and that could release lots of water that may not have any place to go. They're concerned about the Merced River in Yosemite. They're concerned about Owens Valley. They're concerned about San Joaquin Valley. And parts of the San Joaquin Valley already have a lot of water. This is the town of Corcoran. And some of you may have read about Lake Tulare. This was an old lake that used to exist. It was a permanent lake in Central Valley that was then diverted for agriculture and dried up. So Lake Tulare has kind of reappeared from this is just from the rainfall that we had December, January, so that it has built up in this agricultural region, again, creating problems. And the folks in the town of Corcoran are worried because there's a city, there's actually a state prison near there. So this is about halfway between Fresno and Bakersfield. And the blue diagonal shading shows where Lake Tulare used to be. The reddish pink orange is the area that's currently flooded. And that dark black line wrapping around Corcoran is a levee that's protecting the town, but it's eroding. And they're talking about the need to reinforce and raise that levee. And if we get too much snow melt, if it comes in too fast, we're going to, it may come in faster than they can raise the levee to protect it. So hopefully it won't be that fast and they'll be able to protect the town. One other thing on this map, just one little point, there's this town called Allensworth to the south. There's actually a state historical park there. This is one of the first Black communities in California, communities settled by Black people. And there's a historical park there. They've also experienced flooding. And I was kind of struck by this picture of this is near Allensworth. And you've got Highway 43 in the foreground, and behind that, the rail line. That rail line is, they've got a freight train, but that's also the Amtrak line, the San Joaquins. And last fall, I took the San Joaquins up to San Francisco, and very close to this spot, I just happened to snap a picture which is this, again, this is a little ironic. This is you see this all up and down the Central Valley. If you drive I-5 through there, you see these signs, stop dumping 78% of our water in the ocean. And of course, the irony is right now, they would really like to dump 78% or more of the water into the ocean to avoid the flooding risk. So this is kind of the future that we're looking at. We're going from droughts with the farmers complaining about we don't have enough water to these flooding events, which could be very significant. And as the climate continues to warm, atmospheric rivers are going to carry more moisture. And we expect this cycle of droughts, drier weather with longer time between rain events. But when the rain comes, it may be a lot all at once in these kind of catastrophic or very significant events. And I think I'm going to stop it there. I want to be sure to leave time for questions. But that's just a quick overview of what's going on with moisture in the atmosphere. Okay, so not sure.
Thank you.
Stop sharing
That
here.
was great. I felt like I should take notes, but then I realized it's not going to be a test.
I promise no test, and it's being recorded, so you can always look at it whenever you want. Okay. Questions?
Who has questions?
I have a question. So you spoke about El Nino and El Nina, or
La Nina.
La Nina, and on the Atlantic coast, there's the Gulf Stream. Are those changing because of climate change, or vice versa?
Yes. Short answer is yes. The Gulf Stream is part of this big circulation pattern that actually stretches all the way around the world. And there is significant evidence that that pattern is slowing down. And that's because melting ice in the Arctic is dumping a lot of fresh water into the surface, where the water used to be salty. Salty water is denser and it sinks faster. And it's that sinking salty water that drives the whole thing. Some people call it the ocean conveyor belt. Water sinks down, it goes all around, circulates, it comes back up around the Gulf Stream and heads back over. So the Gulf Stream is, it looks like it's slowing down. Big questions about how much, how significantly. One important factor there is the Gulf Stream carries a lot of warmth over towards Europe. So if the Gulf Stream were to slow down, you get less warmth. That might cause Europe to warm less quickly than it would otherwise, than the rest of the world with global warming. Could even cause cooling, but more likely it's just going to warm less quickly. El Nino, La Nina, lots of discussions, no clear, there's a lot that's not understood about those cycles. So a lot of discussions about the impacts, but no clear answer right now on exactly how those might change in a warmer world. But it's very much a topic of active research.
Cynthia, you have a question? Cynthia, you have a question? Go ahead.
Well, I think you more or less covered it just now. Talking about the slowing jet stream and the way it's dipping and undulating, and about the slowing of the Atlantic meridional overturning current.
Yeah, right. That Atlantic meridional overturning current, that's the what I was talking about. The Gulf Stream is a piece of it. So that's slowing because of the fresh water. Let me put up, I've got all these slides that, of course, I always have more slides than have time to get to, but that's fine. It's better to have time for questions. So let me just share the screen on this one. Hopefully you all can see that. There is so basically the jet stream is this high-speed stream of air that circulates around the globe. And it's basically caused as air goes from the rise in the equator. We saw that moisture in the equator in the atmospheric rivers slide. As the air, of course, is rising, hot air along with that, and it sinks down at mid latitudes. And it turns out, because of the spinning of the Earth through something called the Coriolis effect, that air, as it comes down, also gets an eastward push. So it starts to move eastward as it comes downwards. That creates the jet stream. So the jet stream is this high speed, this is not moisture river, atmospheric river, this is sort of a river of air or a flow of air. There is a theory which is not accepted 100%. Jennifer Francis at Rutgers was one of the first people to talk about this. But essentially, the Arctic is warming faster than the middle latitudes and the equator. So as the Arctic warms, the temperature difference between the equator and the poles gets to be smaller. And it's that temperature difference that drives that circulation. So as the temperature difference gets to be smaller, the jet stream may get weaker. And when it's weaker, it tends to get more wavy. So this picture shows a strong jet stream on the left side and a weaker jet stream on the south side. And one of the important things the jet stream does is it kind of separates the cold polar air over the Arctic from the warmer air down below. And when it gets wavy, we get cold air moving farther south than usual and warm air from the equator moving north. So we get these basically big fronts of weather, and we've seen these outbreaks, and people talk about the polar vortex. This is cold air from the polar vortex that's able to slip down much farther south than usual into the United States. And so we get this very cold air going across the US, and behind it, warm air pushing up from the equator where the jet stream is wavy. So this is yet another example of how global warming is changing the climate through this significant change in weather patterns. There's also some folks believe, although it's still very controversial, that these patterns tend to move slower. The jet stream's weaker, so the patterns tend to be more stationary, and that causes some systems to move more slowly. So these cold air systems can hang around for a long time. And there does seem to be a tendency for weather systems in general to move more slowly. Hurricane Hugo in Houston, part of the reason it flooded the city so badly was that it didn't move quickly as it went on shore. It slowed down and dumped a lot of moisture. Same thing with these cold air pockets. They move more slowly, so you're exposed to that cold air for a longer time. So again, you get the folks who are saying, well, this global warming is nonsense. They say it's making things warmer, but it's making things colder. It's making it wetter, but it's making it drier. And the fact is, that's true. Overall, we're getting warmer, but it shifts around where cold air and warm air are. It shifts around where the moisture is. So we do get pockets of extreme cold air where we didn't see them as much before. Okay.
Thank you.
Harriet has a question. Would you like to verbalize it, Harriet?
Sure. Is there any place that's going to actually be unaffected by this? I've read different articles where people say they're moving to Denmark because it's going to be a safe place in 20 years, or they're going to buy land in northern Canada because it's going to turn into a tropical paradise or whatever. I mean, is there any place that's not going to be, that's because of the wind currents, the ocean currents, the land masses, it's not really going to be heavily affected? And how much is land costing there?
That I haven't keeping track on the markets there. Obviously, I'm still staying in California. Yeah, and I kind of have, I'm of two minds about this, because on the one hand, these articles are definitely very clickbaity. It's like, here's the top 10 list of places that will be the best places to move. And the fact is, it depends so much on location. I live in San Clemente, but I live about 4 blocks inland from the cliffs. So I'm way back from the cliffs and way up above the ocean, about 100 feet up. So, it depends so much. It's not like this city is going to be safe and that one not. Denmark, if you're in Copenhagen, rising sea levels could be an issue for you. Basically, every place is going to be affected. There's no place that will not be affected. Some places may have feel that they've had a net positive. Svante Arrhenius was a Swedish physicist who back in 1896 was one of the first people to calculate the warming effect, how much the Earth might warm up if we increase carbon dioxide. And he thought this was dandy. He wrote this paper and he said, well, this is going to take several hundred years. You know, he really underestimated there, but it'll be great because my great-great-grandchildren will get to have a nicer, warmer climate than, you know, we're currently suffering through in Sweden. So generally, farther north is, you know, climates are going to move farther north. The idea that there's some talk that by 2050 or so, the climate of San Francisco may be more like San Diego was, and San Diego will be more like some places farther south. So if you want to stay cool, you might want to move north. I mean, this is, for us, it's just kind of a, hey, that's kind of a fun idea. Where do we want to move? If you're living in a less developed country where you don't have an easy way to move, and especially along the belt near the equator, where some of those places may become very, very difficult to live during the summer, it's not as much fun. But yeah, basically the idea is away from the ocean is probably better in terms of sea level rise. Moving north to kind of keep the climate you have or to get to the climate you want. So that there are definitely going to be winners and losers. Personally, I wouldn't be investing in real estate in Florida. There's rising sea level. There's a lot of porous limestone under the soil in a lot of areas where even if you've got a seawall, the water can seep through the limestone. So there are areas, certainly the Gulf Coast and the Atlantic coast are going to be especially hard hit. California is going to be especially hard hit in terms of erosion right on the coast, sea level rise on the coast, and of course, wildfires and the air quality issues that go with those. So every place is impacted. And my personal thought is I wish people would put more energy into trying to reduce future climate change than into figuring out where can I go so I'm going to be safe. That's a long answer to a short question.
Thanks, Jonathan. Kathy, would you like to make your positive comment? Kathy Lambert. Maybe she had to leave, but she's
I'm still here. Sorry, I'm just clumsy with the buttons. I threw my shoulder out. My question is, well, first of all, it's an excellent presentation, and I would listen to it again anytime. I'm glad it was recorded. But I was curious about if it's possible to share this with my big kids. Two of them are conservationists. They probably know it, but I think it's such a very concise, clear report that they might enjoy it and have a space to share it. And my third kid has a house in Lake Tahoe, South Tahoe, so I thought she might enjoy that part too.
Yeah,
I can answer that for
yeah, go ahead.
Kathy. Kathy, we will in about a week we'll have this whole presentation on our website, and we'll send everybody here a link to that so you can see it again.
Yay! Thank you.
I was going to say Tahoe. It's been a mixed bag. I was reading the lake is about as clear as it's ever been. Just all the rain kind of flushing things out and killing some of the critters that eat the algae that can cloud up the lake. So I'm just curious about your children's experience. About did they survive the snows? Are they okay?
Well, the good news is they also have a house in San Francisco. So yes, they did. The bad news is they do go very frequently and ski, and my daughter tore up both of her knees. So she's now resting in San Francisco. And I don't know about the house. That's why I'm curious.
So I wanted to I guess Walker Wilson has a comment. Would you like to make that, Walker? Oh,
sorry. Yeah, I accidentally popped that too early. I wanted to make sure till anyone's more relevant questions maybe got asked first, but just wanted to make an introduction. That's all.
Yeah, and I'll just put in a little plug for native plants and xeriscaping, which I'm sure everybody in this group is already on board with. But managing the droughts, we're going to need plants that are able to tolerate droughts. Big lawns are big consumers of water.
Yeah. Okay. Well, I'll go ahead and give my little plug real quick then. Introduced by Deanna, and I'm in Fallbrook, and it's a pretty small location right now. I only have about a quarter acre. One of the reasons she wanted to introduce me to the group is that I'm looking for a little bit larger acreage to grow more plants. Maybe something small, still like 1 to 2 acres or so, but and in the Fallbrook area, I'd love to stay there too. It's a great area. It's a good climate to grow a lot of different plants. I can shoot an address for people to come pick up there, but otherwise, yeah, I grow all different native species, trees, shrubs, bushes, grass, flowers, some endangered species as well. And
Walker, put your information in the chat, and I'll have Mike Bullock ask his question before Jonathan goes away.
Yeah, so I'll just go ahead and leave that in there, and then anyone else can ask their other questions and stuff.
Mike, go ahead.
Yeah, hi, Jonathan. I was wondering if you ever mention in your discussions the possibility of our destabilizing our climate, having kind of a positive feedback situation where things kind of get out of hand and that kind of thing. The Secretary General says we're dangerously close to a point of no return. And he also says we're solidly on a path to an unlivable planet, that kind of thing. So that's my question. Are you concerned about the process of creating positive feedback? The warmer it gets, that kind of a situation.
Yeah. So I guess a couple of things. One is especially when I taught the climate class, I really try to avoid unlivable, uninhabitable, things like that, because it's sort of, we're all going to die, and that's not. Human beings have been around on the earth for a long time. We've been here when it's this warm. Human beings have not been around when it was warmer, but that doesn't mean habitable. It's like, that's not. If that's your criterion, that's not good enough. The fact that some people will be able to live does not mean we've got a just, sustainable, flourishing world. A lot of folks who are in difficult especially around the equator, small island states, their particular areas are going to become uninhabitable. Possibly.
So do you believe that the Secretary General was being kind of an alarmist? He was overstating the problems?
I'd say it was hyperbole. And I think it's really easy to debunk something like that. On the other hand, the tipping point is a real issue. The thing is, there are multiple tipping points, and when climate scientists talk about tipping points, they mean some kind of a change that. If it's not as if, you bring the temperature up and then you bring it back down and everything goes back the way it was. Certain things won't. It's kind of like, if you push a stone off the edge.
Why would it come back down? Let me be real specific. You probably have read about the amount of methane gas that's under the permafrost, and what that would do if a large percentage of that were to be released. Of course, methane is a very powerful greenhouse gas. It would trap a tremendous amount of heat. And maybe I'm wrong, but I think I have read that there's a lot up there. There's so much. And of course, if it starts melting, it warms, and then the warming will make it melt more. Eventually, I don't know what would stop it. I guess it'll just all go, every bit of it will go into the atmosphere. And I believe I've read that would pretty much be the end of everything.
Well, this is a topic where, again, there's a lot of controversy, and I don't know that you could 100% rule it out. The most extreme scenario seems unlikely, that like all the methane goes into the atmosphere, but it certainly is a feedback where, as we warm up, more methane goes in the atmosphere. That enhances the warming. We know that that's happened in past ice ages. as the ice sheets retreat, the permafrost starts melting, more methane goes into the atmosphere, and we can actually look at ice cores and we can see that. But in the past, at least, it's always kind of peaked and then come back down. But eventually, the other thing with methane is its lifetime in the atmosphere is only about 12 years. Carbon dioxide lasts for hundreds or thousands of years. If we can start pulling carbon dioxide out of the atmosphere, and that's a huge if, that would be the thing that would bring the temperature back down. And some people think, oh, we just suck out the carbon dioxide, everything goes back the way it was.
Yeah.
But
By the way, you said that Homo sapiens have lived through a lot worse.
No, I said about the warming we've had now.
Yes, but what about the 420 parts per million carbon dioxide? I mean, that is an outrageous number. It hasn't been that high for millions of years, and so there's large-brained ape that I know that has lived on a planet where the atmospheric CO2, and we're living in a spike. It just went from 200 years is no time at all in the life of a planet, and it went from 280 is where it should be, and it's at 420. And there's no prospects for that not continuing to go up like that.
Well, you have to go back about 5 million years to see a period when it was in the 400s before. I mean, if you go back 65, 70 million years, we're talking about 1,400 parts per million. But it was a very different planet then. There were forests in Antarctica. There were, it was jungle covering the U.S., what we think of as the U.S. now. And so basically, I think people could still live in that, but it wouldn't be nice, and it wouldn't be, there'd be so many people displaced. It would be probably a small fraction what we got.
Has the planet gone through periods of time where it was so hot that there was, we're not going to sterilize the planet. There's microbiology, obviously, but has the planet gone through periods of time where it was so hot that there wasn't very much life at all?
As far as we know, the only time that was true was when the Earth was still cooling. After it formed, there was the surface was molten for a while, and then the crust formed. It took, it took hundreds of millions of years for life to develop after that. Since then, we don't know of any time where there, as far as we know, and again, fossil record gets tricky the farther you go back. As far as we know, there's never been any time when there wasn't life on Earth. So this is, So I do.
We're going to have to make that.
Yeah. Sorry.
We're going to make it the last question. I mean, these are good questions, and we could go on for hours, but would you tell people this is an hour presentation?
Yeah,
but these are great questions. I just want to let people know that next month we're going to have Carl Aldinger talking from the Sierra Club, talking about transportation and whether basically his thesis is, maybe it's more than a thesis, that we're not going to be saved by electric cars. We can't rely on electric cars to save us from transportation pollution, or from, save us from global warming. So that'll be next month. And then, Deanna, are you still here? Deanna just invited, and she accepted Dorothy Wooten to be our speaker, who is our county public health administrator, and she'll be talking about the public health aspects of climate change. We talked about hotspots and what happens to people who are in the lower ends of the income and health gradients who suffer from hotspots, for example, flooding and some other things that Dorothy will be talking about. So thank you everyone for coming. It was an excellent presentation. Thank you, Jonathan, for speaking to us. And we hope to have you again.
Thank you.